All right, we'll come back to that problem in just a second. So here we are. Oh no, that's embarrassing. All my days are off by one. Pretend this says Tuesday. Tuesday, Wednesday, Thursday, Friday. We'll start next week with the Chapter 5 test review. Chapter test to be on Tuesday of next week. All right. So this week we got several things going on. We've got Tuesday, Wednesday. So Thursday, we're going to have a quiz review, first half of class, and then a little Canvas quiz on the fundamental theorem of calculus that might look familiar to a problem that we might start class with today. And then we'll finish the week with a quiz. And for homework, we'll just have some of the test review, and then we'll get into the test review. Go over it on Monday, and then test Tuesday. I'll fix that agenda a little bit later. All right. Speaking of problems that may look familiar, we got a little FTC problem. Now, we've done this before. We did a problem like it. So start the notes for 5-4. All right. You're looking at the F graph. But H is the what? There's multiple correct answers here. What is H representing in this problem? The antiderivative, very good. And what kind of function? Area function. Good. So what did you guys get for H of 0? 0. H of 0 is the integral from 0 to, 0. And I don't care what goes here. That's 0. On what interval or intervals is H increasing? Who can give us an answer and explain? Cole.
0 to 6, because that's the only time the area underneath the curve is positive.
0 to 6. Careful there. Describe it using a function. It's where F is positive. Good. You said area. I think you meant the area under F. So H increases when F of t is positive. And do you remember that? That sounds like a first derivative test argument, doesn't it? Right? And remind yourself of the fundamental theorem of calculus part 1 that says H prime of x, if I take the derivative of the left side, I take the derivative of the right side, which is F of x. Very good. So if I'm looking for where H is increasing, isn't that where H prime is positive? Which is where F is positive. That's your argument there. That's the first derivative test argument. On what interval is the graph of H concave up? Well, let's go down another layer. Ready? H double prime is equal to F prime. Where is H double prime positive? Well, that's where your F primes are positive. F primes are the blank of this graph. Slopes, right? Slopes of this graph. Ready? Help me out with slopes. From 0 to 6. Ready? Positive, negative, 0. Negative. Still negative at 6. How about 6 to 10? Still negative slopes. Negative slopes. What's the slope at 10? 0. The slope of F is 0. And then from 10 to 12, the slopes on F are positive. So where we just answered, that is the same answer to where H double prime is positive. So H is concave up from, I'm saying 10 to 12. That kind of looks like maybe it might be a little bit before 10. Would you agree with that? That's tricky. I would not do that to you. All right. I'm going to say 10 to 12 and then also add shame on them for making it that close. All right. A fair thing would be, if I were writing this question, I would say F has a horizontal tangent at x equals 10, or t equals 10. No, it would be x equals 10. Sorry, x equals 10. That way you'd know, okay, that's the minimum value. After that, f prime is positive. With me? Reason? H is concave up because h double prime, which equals f prime, is positive on that interval. Is that an okay explanation? All right. Where does h achieve its maximum value? Someone else. Huh? What happened? Oh, did it? Oh, sorry. Is h of 12 positive or negative? Who wants to, someone I haven't heard from, argue that point? Is h of 12 positive or negative? And why? No one? Okay.
Looking at it visually, I want to say positive because it looks like there's less negative than that.
It's a great argument. H of 12 is the integral from 0 to 12, isn't it? Okay. Positive, 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 positive. Negative, 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 negative. But I agree with Caden. It looks like however many units I've accumulated of positivity, I only went back, or it got taken away, I wouldn't say as many units as I accumulated. So I would say that's a positive result. A positive result. Are you guys okay with that? Positive. Where does h achieve its maximum value? Dom, what do you think?
X is equal to 6.
X equals 6? What would your reason be?
Well, area is increasing until you reach 6, and then it becomes negative, and then it starts decreasing.
You guys agree? Area increases until 6 and then starts decreasing. If you want to use a first derivative test argument, you could say, because I mean, when you read h has a maximum value, you should be absolutely thinking back to chapter 4 where we did the first derivative test. Okay, we're looking for where h prime of x changes from what to what for a maximum. Positive to negative. Well, h prime is equal to what? F. Isn't it also where f changes from positive to negative? Oh, look, at 6, right? That's a good argument, Don. I like that. Thank you. What's another argument for that? Oh, I'm sorry, not another argument. Another thing to consider is, was there a maximum or a minimum at the endpoints? Okay. What's the value of h at 0? Well, we already did that. What's h of 0? 0. And then what did h do after 0? Did h go up or h go down? H went up from 0, correct? Because it started taking on positive area. Now, how about at the endpoint? How about at 12? Was h decreasing into the endpoint or increasing? H was decreasing into the endpoint, so that makes h of 12 a minimum. Do you agree? Oh, I gave it away. Where does h achieve its minimum value? At 0 and at 12. Now, this is not my final answer. X equals 0, x equals 12. Which one is the minimum? 0, right? It's the absolute minimum. Because of Caden's argument, I would say h of 12 is positive. And if h of 0 is 0, that's less than a positive number. So that must be the lowest. We good? Be prepared for a Canvas question similar to that one later this week. Did I say Thursday? Wednesday. My days are going to be all messed up. Tuesday? Wednesday? Thursday. But today, a one-dayer, the trapezoidal rule. I'm going to fly through this. Do you remember how we estimated area under a function between the function and the x-axis with Riemann sum rectangles? Remember that? Oh, estimating was so much fun. But then we said, there's a way to find the exact area between the curve and the x-axis. Enough rectangles. We'll see you later. And I said we're going to come back to a rule later that's estimating again. And why would the book do this? I think Riemann sums were kind of tedious, a left end, right end, midpoint approximation. I think the trapezoidal rule can also be tedious if you throw it in there with all those other ones. So it's kind of, it gets its own day after we've already found exact area. This is not used that often, and it does have its place. Because what if we have a table of values that you don't know the function? You can't do the antiderivative, plug in b, plug in a, subtract to get area, because it's a table of values. You don't have a function. So it has its place, all right? So the trapezoidal rule, I'm going to do a very, very quick introduction to this. We're going to figure out how to do it, and then we're going to do a couple examples and be done. Ready? Do you remember the area formula for a trapezoid? 1/2 b1 plus b2 times h. Remember that? Half the basis times the height. Now, a triangle is half the base times the height. A trapezoid is half of the bases added together times the height. That's kind of the way I remember it. Now, be careful. Be careful. In case you forget, be careful. All right? What do we call the h? What's the rule for a trapezoid? The bases are the parallel sides. Very good. They're the parallel sides. What's the h? The distance between the bases. So if this is your trapezoid, these would be your bases, wouldn't they? And this would be your h. Make sense? Now, if this is your trapezoid, these would be your bases, and this would be your h. And I actually kind of did this for you before. We did a problem similar to this before, but we're going to officially introduce it today. All right? So very quick rundown. Are you ready? Here we go. Let's say we have a function that looks like this. We go from A to B, and you're told to partition it into, I don't know, 1, 2, 3, 4 trapezoids. Here's how you draw them. This is so much easier than the Riemann sums, okay? Remember Riemann sums? You had to be like, okay, here's my interval. Is it the left height or is it the right height? And do I draw it over and down, or from the right over, left over, and is the left end point right? Remember how it was kind of tricky which way to draw it? And I said, be careful how you draw it. Even some of you guys got points counted off on the quiz for how you drew it. All right. Trapezoid is so easy. Are you ready? You go to the interval. You get the left function height and the right function height. Connect them. Okay. Drop them both down. See the trapezoid? So what are your bases? They are the function height at A and the function height at A plus delta x, right? If this is delta x, then whatever that x value is, it's the height at that function. Ready? Add them together, multiply by 1/2, and then times the, what's this called again? It's your delta x, which is the height of that trapezoid. Are you with me? On to the next one. Well, I've already got this function height. Let's find the function height here. I connect them. I drop them down. Okay, so here we go. This is B1, the first base. This is B2. Do you agree that, now, I'm developing the formula for you so it doesn't look confusing. We're kind of multitasking here. I'm going to go through this quickly and develop the formula at the same time. How many times does the first base get counted? Once. How many times does the second base get counted? Once for the blue, once for the red. It gets counted twice. It gets doubled. And if this is the same delta x, which my picture does not look like it, but it is, then that's going to be the height. And this next one we'll call the third base. And then for the next trapezoid, I've got this height and this height. I connect them. Oh, look. My third base gets counted twice. My fourth base will get counted twice. But my fifth base only gets counted once. Are you with me? So here we go. If there are 4 trapezoids, capital T is used for trapezoid area. Okay, just like we called it RRAM6, LRAM6, capital T. The first trapezoid was 1/2 B1 plus B2 times H. Plus my next trapezoid, 1/2. What's the next one going to calculate? Not B1 plus B2, but good. B2 plus B3 times H. Plus the next one is 1/2 B3 plus B4 B4 times H. Plus the last one, 1/2 times B4 plus B5 times H. Well, if all the trapezoids have the same H, which is nice, we could factor out some stuff. You ready? What can I factor out of every single one of those terms? A 1/2 and a H. Well, 1/2 H is the same as H over 2, isn't it? 1/2 H, H over 2. So what's this going to look like? H over 2, what's left in the first set of parentheses? B1 plus B2 plus B2 plus B3 plus B3 plus B4 plus B4 plus B5. How many times does B1 get counted? How many times does B5 get counted? And all the other ones get doubled. So B1 plus 2B2 plus 2B3 plus 2B4 plus only 1B5. Does that formula make sense to you? Because of the shared sides of those trapezoids, every interior trapezoid gets this, the B's get doubled. The first one and the last one, those ones only get counted once each. And there, my friends, is your trapezoidal sum. All right? It's H over 2. Now, they called it Y naught and Y1 and Y2 and all that. All right? There is your trapezoidal sum. It's easier for me to just show you where it came from than to show you that formula and just say memorize it. Now, interestingly enough, it's the average of your RRAM and your LRAM. It's the average. Geometrically, can you see why? I mean, I think that's kind of an interesting point. Now look, what would happen if we did LRAM? It would be, wouldn't it be this black one? What would happen if we did RRAM? And doesn't that trapezoidal diagonal cut that rectangle in half? You see it? So geometrically, I think we can kind of accept that. Now, I don't want you to do that. I don't want you to find LRAM and RRAM. You're doing things twice and then divide it by 2. No, just do the trapezoidal sum. But back to our driving activity, it wouldn't be that bad to find the trapezoidal sum because I had you do LRAM 30 and RRAM 30, didn't I? Add them together, divide by 2. There's your trapezoidal sum. Which that day we were kind of like, oh yeah, I bet if we kind of average those values together, we'd get an even better measurement. Because what if your starting speed was 0? That doesn't get counted for LRAM. And it might skew the data a little bit, right? The trapezoidal sum kind of balances those out. The easiest thing we're going to do, instead of taking a bunch of notes, I'll be honest, you're going to see this two different ways. You're going to see this with a function and with a table of values. The easiest way to do this lesson is to just do some examples. There's not going to be many notes. Do you understand how to calculate it? Okay, I'm not going to insult your intelligence. All right, let's do this one. Go ahead and solve this. This is a table of values. I bet you could figure out how to do it. The function f is continuous on the closed interval from 1 to 7 and has the values that are given below. Use the subintervals 1 to 4, 4 to 6, 6 to 7. Now listen, I just showed you the trapezoidal sum. When can you use it and when can't you use it? Cole.
You can use it when the intervals are equal.
Did you hear it? You can use that formula when the intervals are equal. What are we looking for? The delta x is being equal. But what if they're not? Just look up here. 1 to 4, 3. 4 to 6, 2. Uh-oh, can't use the formula. What are we going to have to do? Each trapezoid on its own. Add them up. Go for it. You just get 160. Not that bad. So if you have to do 3 separate trapezoids, so be it. And again, you're looking for the delta x's. 1 to 4, 4 to 6, 6 to 7. I would say this is the most common kind of question they're going to ask you on the AP test. If they're going to ask a trapezoidal sum, they're not going to have you memorize the formula for the trapezoidal rule. There will just be like 3 or 4 trapezoids to calculate the areas of. All right. And I took some release questions for you. Here they are. A little application here. I would encourage you to work with a table partner. All right, we're gonna pause for a second. Is anyone completely lost as to what's going on here? little bit. Okay. Last week we talked about. Well, first of all, I don't want to give it away. Who can help us out and explain what this is telling you to calculate? What's this called from last week? Absolute value via t. It wasn't displacement. Total distance traveled, right? Total distance traveled. So when it says using appropriate units, explain the meaning, I told you last week, they're going to ask, what does this mean? How's it used? It's the total distance the car traveled between 30 and 60 seconds. That's the meaning. That's the meaning. And now we have to approximate it using a trapezoidal approximation with 3 subintervals determined by the table. Okay, so your eye should be drawn to this section, 30 to 60, right? Are we going to use A of t? No, we're going to use B of t and t. This negative 14 should be considered what? Positive 14, absolute value of V of t. Negative 10 should be considered positive 10. So if you really want to, until you get really comfortable with it, you could 30, 35, 50, 60. At 30, I want to graph a velocity that's 14. 30, 14. At 35, I'm going to graph a velocity that's 10. At 50, 0. And at 60, 10. Won't the area of those trapezoids replace the integral? You following me? I don't know how to find an antiderivative of a table, and you don't either. But they're not asking us to do an antiderivative. They're saying use capital T to approximate that. Go for it. Can you take the antiderivative? So here there's no option. You just have to just use either RRAM or trapezoidal sum or an LRAM or something like that. But what if it's a function that you're like, oh, I know the antiderivative of that? Then yeah, you're going to take the antiderivative, plug in B, plug in A, subtract. So it kind of depends on the scenario. But if it's a function that's easy to antidifferentiate, it's probably going to do that approach. We call that fundamental theorem part 2. Does that answer your question? All right, you didn't have to draw this out. This is just to help you. Now, technically, those are 2 triangles. I mean, you could call it a trapezoid and call one of the bases 0. That's fine. It's going to end up being a triangle. What'd you guys get? I haven't done it yet. 185? 185 will be the correct units. I hear one person. Everybody else. Feet. 185 feet. If I can't emphasize enough, practicing writing this out into a sentence for them. They're going to have you justify your answer. The car traveled a total distance of 185 feet. Don't stop there. On the interval from 30 to 60 seconds. That would be a perfect answer. Full credit. You use the context, total distance, and you use the time interval. Make sense? Awesome. Next one. Go for it. Can you guys see that all right?
Yeah, that's it.
All right. Let's just pay attention, which is the only thing some of you guys did, to this part right here. Integral from -3 to 15 using 6 subintervals of equal length, and we're using the trapezoidal approximation. So back to Dom's question. If I wanted to find the antiderivative, okay, this is called f. Wouldn't I need to know capital F of 15? Like, wouldn't I need to know capital F, plug in 15, minus capital F of -3? Correct, Dom? I don't know what that function is, so I can't do that process. I can't use an antiderivative here because I don't know the function. Even if I did, I may not even know its antiderivative. So they don't want us to do that. They want us to use the trapezoidal sum. So the trapezoidal sum can replace the fundamental theorem of calculus part 2, which is to find area under a curve. So here's the first trapezoid. It goes here, here, and gets connected. Do you guys all see it? Okay. The next trapezoid goes here to there. What's our net area so far? From -3 to 3, our net area is 0. With me so far? Next one. Here's the next trapezoid. Down, down, connect. Well, it's half of B1 plus B2, up to 4, times H, 4 times 3 is 12, times a half. So what's the area of this trapezoid? 6. Do you agree? This area is 6. I could write those in. They're going to cancel. What's the next area? 6. What's the next area? Okay, so you went ahead and did that. That's fine. So the integral by itself in its own context, the integral from -3 to 15 of f of t dt was what? 12. Okay? But they defined G to be something a little different. How is that different? Now, I think there were more parts to this problem originally. So this may not affect what we do eventually. I just want you guys to understand what's going on. All right, they're gonna do this to you. So let's walk through this. Let's break down G. I know a couple values on G. Okay, what's G of 6? 5 plus the integral from 6 to 6. Why did I pick 6? For that reason. Of f of t dt. So G of 6 is 5 plus 0. 5. G of 6 is 5. Are you with me so far? This is a terrible time because I need you guys to focus. What if they asked you for G of 15 or G of -3 or whatever? Okay? Here's what I want to relate this to. Remember how I asked you, you love watching me walk in front of the room. What if I said, okay, I started here, I got displaced 12 units to the right, and then 16 units to the left. My total displacement was -4, wasn't it? But if I say, where am I? You need to know where I started. Or some position along the way. Do you agree with me? So what if I say, what's g of 15? G of 15 is, ready? I have to start here because that's the value I know. I know g of 6 is 5. So ready? 5 plus 6, I'm up to 11. Plus that, minus that, I'm still at 11. G of 15 is, it was 5 plus the integral from 6 to 15 of f of t dt. That's 11. Okay? What's g of -3? Okay, I have to start at 6. What was g of 6? 5. Where am I now? I'm at -1, aren't I? Because think about it. If I knew where I was here, I would add 6 to it to get where I am here. Well, to go backwards, I need to subtract. So I'm at 5. Here I must have been at -1. What's g of -3? -1, and that's not the same as -1 as this -1. -1 is a position. This would have been a velocity. Okay. So g of -3 is -1. Does that have any bearing on that? No. That's a displacement question. What's my integral from -3 to 15? It's my net number of units that have been accumulated. Are you with me? Be honest. I'm going to say it again. This right here is me walking in front of the room. Okay, I went 12 to the right. I went 16 to the left. What's my displacement from where I started? -4. Did it ask where I am? Did it ask g of this? No, it just said find the area. If I wanted to know where I was at 15, I would need to know a position along the way. That's why they told you 5 plus. Please tell me you understand part of that. Okay, good. They will, and they're going to try to piece it together for you. They might. These are usually asked in reversed order. Like they'll ask you for the total displacement first, like a part A question, and then this will be like part B, and then they'll ask for like the derivative at a certain, like g prime of 6. I don't know. They'll do stuff like that. Okay, so it's so important. Last problem for today, and then I'll give you the homework, which is not a whole lot. I don't love the problems in the book. That's why I'm putting these during class. I think these are better. These are better questions. Must get an answer. Can we use the trapezoidal formula, or do we have to break it up into separate trapezoids? Break it up. What'd you guys get? Are these the calculations you got? What's the total sum? 621. Good. What are the units? And it's not the average. It's the number of people that have waited in line during the time from 0 to 4. Okay. Oh, I'm sorry. No, it is average number. Sorry. Average number of people waiting in line. Okay. Because their function was people per. What were the units? Oh, it was measured in people. Okay. Measured in people. So. Hold on a second. We're going to have to find an average here. We'll pick up here. So what's the area? What's the area under a people function? So how would you find the average number of people? Did you divide by 4? All right. 155.25. All right. Now it's on the correct days. All you have to do is page 312, 5 through 7 and 9. 5 through 7 and 9.